Now we will start with a moving coil galvanometer. That galvanometer is mainly used to measure a very small amount of current in the electrical circuit. So now how exactly it works? So let's say that. So we will see the construction for that also. Before that, we will see a very important point. So what will happen when you just place that your loop? So we have just seen that when you place that current carrying conductor in some external magnetic field, it is going to experience some force. But now if you place some loop in some external magnetic field, or you can say that, so definitely this is the loop which you have to place in some external magnetic field, and the current is going to flow through that loop. Yeah, so definitely let's say this is the direction of current, and let's say this is the external magnetic field which has been produced by this strong magnets. Yeah, so this is the direction for your, you can say that, your magnetic field, how we can show it. So definitely now this parts, so this A, B, C, D, so these are the different parts. DA also part of the loop. So in this case BC and DA will not experience any force because they are parallel to that external magnetic field, and at the same time if you consider the force experienced by this AB and CD, they are equal and opposite. So let's say you can say that this is nothing but the F1 and F2. So these are the two forces experienced by this AB and CD, so which are equal and opposite. They are separated by some distance D, let's say, and again I can say that the length for each of them, it is nothing but the B over here. So the length of AB and CD is nothing but the B. Then I can find that torque. So torque is nothing but, we know that magnitude of the force F is equals to, that is the ILB. Yeah, so this is nothing but the ILB. Yeah, and again this is what I can say that for this ILB, obviously this B you have to take, that is nothing but the value which is nothing but denoted in the capital. So I can just say that. So this is your ILB, and again what is the perpendicular distance? Yeah, so that torque, let's say it is F into perpendicular distance. So for this case, so let's say perpendicular distance is D, then F is equals to, that is the same thing. Yeah, that is a I, then that is nothing but the length. Yeah, so this is your length is, I have just considered B, and then this is a capital B external field. Then this torque is your IBB into D. So this B into D is nothing but your area. So definitely that is a I, again area into B. So this is the torque. Again that is a M, that magnetic moment. We know that M is equals to I into A. So definitely I can say that now this torque become your M into B, or you can say that torque is equals to M bar cross B bar. So this is the expression that we have derived for this case, which is the cross product of your M and B. Again the same thing that you can do. Consider the different cases, the angle based on that you will get the maximum value for the torque when the angle theta is 90 degree. Yeah, so you can find the value for that torque. Again one more important thing that you can do, if there are n number of turns, so according to that the force is also that n number of times, which you can find it out, and according to that you can find the value of that torque. Now if you want to find that energy of the dipole, yeah, definitely that energy also sometimes that we required. Yeah, so that means simple, that energy means definitely you have to do some work against that external magnetic field. Yeah, so that is nothing but you can say that for your external magnetic field, so which you required to store it, and that energy is nothing but your minus M bar dot B bar. So this is the energy for your dipole. Yeah, so that is nothing but you are going to do some external work, and that external work will just save in the form of your energy, so which is the principle for your energy of the dipole. The same thing is also that is exist for your this for your related to the electric field, and this one is also that is exist for your magnetic field. So where you can say that U is equals to minus M bar dot B bar. So again you can consider the different cases, the value of 0, 90 degree or 180 degree. You can find that for 180 degree the energy is positive for that case. Now we will see the working of ammeter. So why just we need that ammeter, as we have seen in the moving coil galvanometer. So if you just see the construction for this one, so there is one that coil, moving coil, and when the current is going to pass through that coil, definitely it will experience that force and there is a formation of torque, and that coil is going to twist or rotate, but there is a maximum limit up to which it can rotate. And so after certain you can say that if there is a more amount of current, so there is a possibility that that coil might get damaged. So to overcome this, I'm just going to overcome this by just using this your ammeter. So what we are going to do over here, I'm just going to use one resistance that will be in parallel, which we are also going to call it as a shunt resistance. The total current which I have to measure for this particular case is nothing but your I. Then let's say out of that I, again we can say that the Ig amount of current. So that Ig amount of current which is going to flow through that your MCG, which is nothing but moving coil galvanometer, and rest of the current will flow through this your shunt resistance. So when we can say that, so these two are in parallel, then according to that, so they are connected in parallel. So I can say that this I minus Ig into S, again Ig into G, both the, you can say that, so their voltage is same since they are connected in parallel. So from this, based on the value of I, so which you have to just, that ammeter which you are going to design for, so you can define the value of your S. So further if you simplify it, so definitely we will get that Is minus your Igs, again that is your Ig into G. Further again, so that Is, so this is your Igs plus Ig into G, Ig taking common, that is a S plus G, so this is I into S. So again that is a S upon S plus G is equals to Ig upon your I. Or further again you can say that, so Ig is equals to S upon S plus G into your I. So this is how we can just find the value for that your Ig. So the fractional current which is going to flow through that your galvanometer. At the same time we can also define the value for your S also. So likewise, so S we can say that which is Ig into G. So this is how we can just write it down. So let's say this is nothing but your Ig, for example, which I'm saying, which is again by multiply your G and upon I minus Ig. So this is how, based on the value of your this resistance S, we can measure the value of your I. So this ammeter, definitely it can increase the range of current, for which you're just using that device. With the help of MCG you can measure up to only limited current, but with the help of now ammeter, so you're just going to connect one more resistance in parallel, so with the help of which you can increase its current carrying capacity. Obviously that Ig that you have just designed whatever, so it will show that Ig only, but definitely by connecting that resistance S in parallel we can measure the total current. So this is how this ammeter is going to work. Again the same MCG we can use to measure the value of your voltage also. So in this case we are going to connect one resistance in series. So definitely again we know that, so they are connected in series, so the same current Ig will flow through this your R also. So the total voltage we can again say that the voltage across this MCG plus your voltage across this resistance. So again with the help of this value we can calculate the value of your total voltage V. At the same time, or you can say that, so this is Igg, and which is again R into your Ig. So further I will say that, so this is V minus your Igg upon your Ig, which is nothing but your R. So further I can say that, so this is V upon Ig minus your G, which is equals to R. So this voltmeter, which is again going to increase the range of the voltage, for which you're just using that device. With the help of MCG also we can measure the now value of your voltage. So and again we can increase its capacity by adding one resistance which will be in series with that your mcg. So based on the value of your voltage which you have to measure, so you can just design the value for this R. So this is how this voltmeter is going to work. According to this formula also, that you can find the sensitivity for this. So that is nothing but theta upon I, which is BAN upon C. So I can increase the sensitivity. So that means sensitivity means simple, how small that it can measure the value of current, how sensitive that your galvanometer is, how small changes it can detect. So that is nothing but the sensitivity. So that is nothing but BAN upon C, so which is directly proportional to external magnetic field, area of that loop, and is the number of turns. C is nothing but that constant. Again, the voltage sensitivity you can define, that is the theta upon IR. Yeah, so this is the expression for your current sensitivity and voltage sensitivity for that moving coil galvanometer.